Hello and welcome to a revision session from the Further Maths Support Programme. Today we're going to be looking at Edexcel Mechanics 3, and this is the third part of the Edexcel M3 course that we're going to be looking at, and we're going to be covering today circular motion. In the sessions that we're going to be doing for Edexcel Mechanics 3, we're going to be covering a range of different topics across the full specification. Today we're doing the Section 3 circular motion work, but if you're interested in revision for any of the other modules, videos are also available for those. Okay, so first of all we're going to take a look at the specification from Edexcel for the circular motion material. And this tells you the things that you need to learn. You need to have the concept of angular speed or angular velocity. You need to know about the two forms for the radial acceleration, r omega squared and v squared over r. You need to be aware of questions that involve horizontal circular motion, which is also motion with constant speed. And you also need to look at motion of a particle in a vertical circle, and you need to be able to look at different ideas associated with those two main concepts. Okay, so let's revise horizontal circular motion first of all. This is just a quick review of the techniques that we're going to be using. We generally have a diagram. It's quite difficult to do these questions without a good diagram, and we usually draw the diagram from the side elevation so that you can see the vertical forces acting in the system. Generally, for horizontal circular motion, there are only two techniques that you can apply, and that is to consider the forces balancing in the vertical direction, because there's no motion in the vertical direction for this particle, and also you need to think about using Newton's second law radially. You have a constant acceleration towards the centre of the circle that's provided by some kind of central force, and you need to use Newton's second law in order to be able to assess that. A few little ideas that you may find useful. Do keep an eye out for right angles. Often these questions will be set up with Pythagorean triples in there, which will make the calculation of radius, etc. easier, so do look out for those. Make sure you include the weight in the vertical direction. Sometimes that gets left out. Don't include anything to do with the weight in the horizontal direction because it acts entirely vertically. And here's the really crucial one. It's absolutely vital that when you're working on horizontal circular motion questions, you only ever consider the acceleration and forces, etc. in the horizontal direction, or the balance of forces in the vertical direction. Any other angle to the horizontal or vertical will cause a problem because it will have components of acceleration which complicate the system. Formulae that you need to remember: linear velocity along the along the circumference is equal to the radius times the angular velocity, and our two formulae for radial acceleration that we mentioned when we were looking at the specification, r omega squared and v squared over r. You have a choice of which of these two you use depending on the question that you're being asked and the information you're given. Okay, so let's take a look at some questions. If you want to pause the recording at this point and have a go at the question yourself, please feel free to do that. I'm going to be starting the solution to this in just a moment, but if you do want to work through it, then it's a good time to pause and to do that. Okay, so looking at the forces that are going to go onto the diagram here. In the vertical direction, we know that the mass of this particle is m, so its weight is going to be mg. And then we're told that we have tensions in the two strings. I'm going to say that the tension in this string is given by TA and this one by TB. Don't make the assumption that those two tensions are the same, because we'll end up without equilibrium in the system. I'm going to put a little bit more information into the diagram. I know that because the two strings are the same length and I have a right angle in here, that each of these angles is going to be 45 degrees. And that gives me quite a bit of information about the system. I'm also going to pop in a radius to the circle here. And again, looking at this right angle triangle in the top half here, I can see that the radius of my circle is going to be L sine 45, or L over root 2, and we might find that useful later on. Okay, so we've got to find an expression for the tension in AP and an expression for the tension in BP. This is what we're looking for. We said on the previous slide that there are only ever two techniques that you can use, and in this case we're going to need both of them. The first one we're going to need is we're going to look at the vertical direction, and we know that in the vertical direction there's no movement. The ball stays in that horizontal circular path, so there's no motion vertically, which means that the forces must balance. Upwards we have a component of TA, which I'm going to say is TA cos 45. That must completely be balanced by TB cos 45 plus mg in the downward direction. I'm just going to do a little tidy up on that. We know that cos 45 is 1 over root 2, it's one of your standard angles, so I'm just going to convert cos 45 to 1 over root 2, and I'm going to multiply up by root 2 on both sides, so I end up with TA minus TB equals mg root 2. That may not necessarily be obvious why I wanted to do it like that, but I think you'll see in a minute why it's useful to have it in that form. Okay, so we've done as much as we can in the vertical direction. Now we're going to try the horizontal direction. So horizontally, we've now got no balance of forces. We've got an acceleration towards the centre, so we're going to use Newton's second law here. The force towards the centre, the resultant force in the horizontal direction, is a combination of components of TA, so TA sine 45, plus TB sine 45. Obviously the weight won't come into it because it's vertical. That's my resultant force towards the centre. And we're given in this question an angular speed omega, so it's going round at omega here. Oh, actually this arrow shows it going the other way, but calculation's the same. So we're going to use the r omega squared version of the acceleration towards the centre. So using Newton's second law, resultant force towards the centre is mass times acceleration in here, and we can also replace our radius here with L sine 45. In fact, I'm going to do that right here. I'm also going to multiply both sides by root 2 because again I know that my sine 45 here is 1 over root 2. So I've got TA plus TB this time. You can see now why I put the first equation into this format. And that's going to be ml sine 45 omega squared, and I said I'd multiply by root 2, and actually you can see here that the sine 45 and the root 2, they're going to cancel each other away anyway, so I'm left with TA plus TB is ml omega squared. And I hope you can see now that we've got two tidy little simultaneous equations. If I add those two equations together, I'll eliminate TB, and I'll get 2TA is ml omega squared plus mg root 2, which means that my TA, that's the tension in the top string, is going to be m over 2, just factorising here, L omega squared plus g root 2. So that's my tension in AP. And if I subtract the two, I'm actually going to do equation 2 minus equation 1. If I subtract one from the other, I'm going to end up with 2TB. The TA's cancel this time. That's going to be ml omega squared minus mg root 2. Very similar structures for these two tension expressions, which leaves me with TB is m over 2 L omega squared minus g root 2. And it's worth having a quick check here. You would expect in this system that the tension in the top string would have to be larger than the tension in the bottom string, because the tension in the bottom string has mg helping it to balance the tension in the top string. And this makes sense, doesn't it? These two expressions are identical except for the fact that TA has a sum in the middle and TB has a difference in the middle. And hence we've got, we can see just by looking at it that TB is going to be smaller than TA, so it sort of offers us some reassurance that we may well have done our algebra correctly. Okay, I'm going to go on to the next part of this question. Again, if you'd like to pause at this point and work through the question yourself, please go ahead. I'm going to work through the system here. I'm just going to add in here, obviously if we were working through this on the exam paper, we'd have our expressions for the two tensions available to us. So I'm going to say that TA is m over 2 L omega squared plus g root 2, and TB is m over 2 L omega squared minus g root 2. And let's have a little think about the system here. We're not being given any extra information to start B with, so we must have all the information we already need. What we want to do is think about when this system is stable. So when this system is stable is working around in this horizontal circle here, if something were to go wrong with the system and it were to collapse, the way that it would collapse would be for P to drop downwards. The particle, the ball here, would drop downwards, and that would happen if the string in the lower part here went slack. It's impossible for the top string to go slack. Even if the system collapses altogether into equilibrium, the top string would still have tension in it. So it must be that the system will fail if the bottom string loses tension, if that goes to 0. So we need to look at our TB here, our tension in our lower string, and say in order for the system to be stable, to keep performing this horizontal circular motion, then that tension there has to be greater than 0. And if that's the case, we can cancel the m and the 2 because we know that they can't be 0. That gives me L omega squared is greater than g root 2, and hence omega squared greater than g root 2 over L for string BP to remain in tension. So just giving the examiner a little explanation of why we know that that works. Okay, so let's go ahead and have a look at the vertical circular motion section. Again, in vertical circular motion, we're using some of the ideas that we had in our horizontal circular motion. The idea of acceleration towards the centre continues. So our radial acceleration here, v squared over r, or r omega squared, is just the same as it was for the horizontal circular motion. And we're also using Newton's second law in the radial direction, just as we were in the horizontal motion as well. But this time we can't use balanced forces because we're looking at vertical circles here. The forces in the vertical direction certainly don't balance. The forces, if you like, into the plane of the circle do balance, but it doesn't give us any useful information. So what we do use instead is conservation of energy. And again, with vertical circular motion, really these are your two important ideas. So those are the two methods that we're most likely to be using here. We add in a little extra dimension to the vertical circular motion by thinking about conditions for full circles to be completed. And the conditions for full circles to be completed depend on the system that you're looking at. The most common, perhaps, is the particle on the end of a light inextensible string. And in that case, in order for full circles to be completed, there must be enough energy in the system for the tension in the string to remain greater than 0 for all values of theta. So as the object goes around the circle, the string must stay taut at all times, or be at worst 0 tension all the way round. Similarly, for something moving inside a hollow sphere or cylinder, the reaction force between the surface and the object moving around must be positive for all values of theta in order for it to stay in contact with the circle all the way around. The slight difference is the rigid rod situation, because it's not possible for the rod to collapse. It can be under a thrust instead of in a tension. So for the rigid rod to complete full circles, you need sufficient energy so that the velocity of the particle as it goes across the top here is greater than 0. And that's the condition for the rigid rod system. Most systems can be reduced to one of those three cases. So let's have a look then at a question here. Again, if you'd like to pause the recording and work through the question at this point, you are welcome to do so. I'm going to start this solution by putting some extra information onto my diagram. I'm going to put a vertical in there and a horizontal in there, and just show my right angle here. I'm going to label the radius there A, and I'm going to put the weight into the diagram and note that the tension is already there. Okay, so we're trying to find an expression for v squared here. Good practice at this point to read ahead in the question and notice that in a minute it's going to ask me for an expression for t. Now if it's going to ask me for an expression for t in a minute, the chances are I'm not going to be using Newton's second law for the first part of the question, because I'm later going to be looking at the value of one of the forces. So we can conclude from that if it's not Newton's second law, the chances are it's probably going to be energy, and that's kind of backed up, reinforced even more by the fact that we've got v squared here, which is the expression that we often get out of half mv squared, the kinetic energy calculation. So for part A, I'm going to go ahead and use conservation of energy. So by conservation of energy here, we've got, just thinking about the energies that we've got going on, I'm going to start initially, so the particle starts from here and it starts only with kinetic energy. When it gets up to this new position here, it's going to still have kinetic energy because it's still moving. It's also going to have gained some gravitational potential energy. So we're going to equate the initial kinetic with the final kinetic and gravitational. There's no extra work being done to it to change the level of energy in the system, so we know that those are equal. Right, initial kinetic energy then is half mu squared, and we know that u squared is 5ag, so I'm just going to go right ahead and put that in there. So half m times 5ag is my initial kinetic energy. My final kinetic energy is going to be a half m v squared, and that's the v that we're looking to find the value of. Gravitational potential energy is going to be mg times the height that it's risen through, and that's this height here that I've shown on the diagram. And you can see, looking at this right angled triangle here, this is theta here, so this is also theta here. I hope you can see fairly easily that the height it's risen through is mga sine theta. Because the radius here is the hypotenuse of the circle, that height there is going to be a sine theta that it's risen through. We can do a little bit of tinkering to simplify this here. We can get rid of all our m's, and we can double to get rid of the halves, and I think you should be able to see that that leaves you with an expression for v squared, which should look like 5ag minus 2ag sine theta. And I'm just going to show off a little bit and factorise that. So ag 5 minus 2 sine theta. You don't have to factorise it for the marks, but as I say, I'm just a bit of a show off with these things. So that's my expression for v squared. For part B then, well, I mentioned that we've only got two techniques, so we're going to use our second technique here, Newton's second law in the radial direction. Only ever using Newton's second law radially for this particular module. So Newton's second law radially, we need our resultant force towards the centre, and you can see here that all of the tension acts towards the centre of the circle. And we've also, and this is very important, we've also got a component of the weight in the radial direction. Not all of it acts radially, but we've got a contributing factor of mg sine theta component of the weight acting towards the centre here. So that's our resultant force. Using Newton's second law, that's got to be mass times acceleration, so I'm going to use mv squared over a, so v squared over r, the acceleration towards the centre. And I'm actually going to substitute in my expression for v squared that I had from part A, and that's going to give me mg, the a's cancel, 5 minus 2 sine theta. And then all I need to do is rearrange that by taking mg sine theta away from both sides. That's going to give me t equals mg times 5 minus 3 sine theta on this side. And that's my expression then for the tension in there. Let's go to the next part of the question. Again, if you're pausing and working through yourself, here's a good time to do that. Okay, I'm just going to transfer my expressions. I had v squared is ag 5 minus 2 sine theta, and my tension was mg 5 minus 3 sine theta. Now I've got to prove that P moves in a vertical circle. There are a number of different ways that you can express this. We said on a slide a couple of slides back that in order for a particle on the end of a string to complete full circles, we need to show that the tension has to be positive all the way around. So for complete circles, oops, excuse my handwriting, for complete circles, t has to be greater than 0 for all theta. Okay, and we know that t equals mg 5 minus 3 sine theta. Now that expression is minimized when sine theta is maximized because we're subtracting it here. So we can say this is minimum when sine theta is maximum, which is value of 1. So T min equals mg 5 minus 3 times 1 is 2 mg, and that's greater than 0 for all theta. And that's what we need to do in order to show that it completes full circles. That confirms what we said in our initial statement here. We have to then find the maximum speed of v. Now, because energy is conserved in this system, you're going to get the maximum amount of kinetic energy when you've got the minimum amount of gravitational potential energy, and that happens down here at the lowest point of the circle. So our maximum velocity, Vmax, again going back to our expression for v squared here, Vmax is going to occur when theta is either minus 90 or 270, or minus pi by 2 or 3 pi by 2 if you want to work in radians. So ag times 5 minus 2 sine, I'm going to go 2 sine 270, and sine of 270 there is going to be negative 1, so we've got ag times 5 plus 2, which is 7 ag, and it does ask us for the maximum speed. Sorry, I should have put v squared max in there. It's asking us for the maximum value of v, so we do just need to take that square root there. Maximum value of v is going to be the square root of 7 ag. Okay, well that brings us to the end of our session. I hope you found it useful. This session was brought to you by the Further Maths Support Programme. If you haven't seen what we do, it may be worth a visit to www.furthermaths.org.uk. Bear in mind that there are other recordings available for different modules under the A-Level Further Maths. I hope you find that useful, and thank you for watching.